All right, good morning, everyone. Thank you very much for having us here. My name is Maurice Naiman. I'm representing Multimatic for our contribution to the fourth AutoCFD workshop. And as Vangelis said, our presentation is on the applicability of solution-adapted grid refinement. This is a method that we use in-house, so I'll take us through how we actually set that up a little bit and some of the results that we generated for it. Just before that, a little bit about us at Multimatic. So we're a relatively small part of Multimatic overall. The Multimatic Aero Group are 3 full-time engineers. There's myself, my coworker Lucas, who's here with me today, and then our lead engineer Elio, who is sort of holding the fort down back in Toronto. In general, our primary focus is a wide range of automotive CFD, but we really focus on full vehicle, external, and cooling flows. So this might be high performance vehicles where we care about downforce and balance. We've done some EV work and a lot of cooling architecture. And then we also have some other sort of side jobs. We've done a whole bunch of internal aero and HVAC CFD, some thermal modeling, some support for our damper business. And then also we've been getting into some multi-phase flows. And then finally, for all of the big programs that we have at Multimatic, we're the engineers responsible for carrying out both scale model and full-size wind tunnel testing. So we really oversee a lot of the aero development from start to finish, ideally, for the programs we work on. And within the CFD program range that we have, there is a huge spread in the type of cars. We do everything from BEVs, so a lot of drag focus, as we sort of see with AutoCFD, all the way up to high performance road and track only cars such as the Ford GTs, the GT Mark II, GT Mark IV, and then all the way into motorsport. So for example, we did a lot of work on the aero development for the Mazda DPI, Lucas specifically actually for that. So now I can actually jump into our contribution. So what we wanted to do here is to use case 2 to evaluate the efficacy of the solution adapted method. We call it gradient-based mesh refinement, or GBMR, which is an in-house method that we have to refine a lot of our volume meshes. So we obviously used the workshop mesh as sort of our benchmark, but we compared these results to an in-house wake box mesh, as we called it, which sort of has your traditional wake box only refinement. And then we also compared it to our in-house GBMR refined mesh. All the meshes that we used were also generated in Hexstream to keep things consistent, but there were some overall differences in resolution around the wheel wakes that Vangelis showed, and then also just our boundary layer. So that's the main reason for having our in-house wake box mesh. It's more to show that true delta, because you'll see some differences between the committee mesh and our GBMR mesh. Overall, the cell count went down for our meshes, but a big part of that is due to the boundary layer resolution and the tire resolution, as I mentioned. But the overall quality of the mesh is very consistent. No big changes in non-orthogonality. Our skewness is quite consistent. We are using an open foam-based solver. We're using K-Omega SST DDES for all our simulations. 2.5 physical seconds, or 2.5 seconds of physical time is simulated. We're averaging for 1.5 seconds. It's a little short. We realize that, but it's trying to be in line with what we tend to do on a lot of other programs for sake of computational resources. So just to sort of explain how the GBMR workflow works, is we would typically begin the process with the simulation on a coarser mesh. We've done enough studies to show that it can be a finer mesh if you want it to, but it doesn't have to be a fine mesh to generate this volume. The GBMR volumes tend to look very similar when they come out at the very end of the process, which basically means that our finest wake box refinements aren't present. It just makes the simulation run a little bit faster to generate the refinement volume. This gives us an estimation of our fields, mainly our total pressure coefficient, CPT, and then the magnitude of our velocity gradients. Then we process our flow field in the following steps to get our GBMR. So we remove a lot of the free stream content. This is clipping done based off an upper total pressure limit, and then also a min and max velocity gradient. We then divide that region into a high and low energy subregion and do a little bit more velocity gradient clipping on our high energy region. And then we combine them back together, do a little bit of post-processing on it to get it ready for CFD input. And then there's our GBMR. And I think the value added of this method is that ideally, and how we use it at Multimatic, is this refinement volume tends to get used for cars of very similar geometry. So in the case of this workshop, the GBMR that we generated for case 2A, we also used it for case 2B to show that there is applicability in using the same sort of overall wake refinement regardless of minor geometry modifications. So to visualize the process, here is our coarser in-house mesh that we would have started with. The key thing to note is that we're missing sort of this finest wake box here. It really just saves us cell time. Then we'll remove a lot of our free stream content, and you can sort of start to see the areas where we see the largest gradients, there's the highest energy, and the characteristics that actually matter. We then divide out our high energy region on the left and our low energy region on the right. We do a little bit more clipping to the high energy region, so you can see we're taking a little bit of content out. And then we combine these regions back together, and we do a little bit of post-processing. Now, I haven't mentioned any of the values we use for all this clipping. It's because it's a little bit proprietary for us. We've correlated it to a lot of in-house programs. And you'll also notice that in the final post-processing, we cut out a lot of refinement around the ground plane. This method was mostly designed for moving ground simulation. So once you have the stationary ground, it gives higher gradients than we normally expect. So we use a little bit of CFD engineer practice to delete some of the ground refinement. That way it wasn't over-refined. What we felt would be over-refining the simulation. So just to compare the mesh, where you can really see compared to our in-house wake box mesh to our GBMR mesh, it really cuts out a lot of your refinement in here, but it also shows us there are some important wake features that are extending downstream of the car that a traditional wake box might not capture alone. So we are starting to see some good physics-informed resolution as a result. And then also along the car's X-planes, you can see it gives a little bit more refinement than a wake box alone might around the tires, but it also saves us some cell size up top in our wake where we might not need it. Now, to get to the point that everyone actually cares about is how does this affect our results? So one thing to note, the blue is the committee mesh, the red will be our in-house wake box mesh, and the purple is our GBMR mesh. What we see in drag especially is that our wake box mesh and our GBMR mesh are very consistent, which despite really changing how we've refined the wake and where we're placing cells in a number of areas, we're actually managing to keep very similar predictions both in drag and then honestly across the board. So that's good to see from the baseline, is that this method isn't really changing our results, but it is giving us more intelligent placement, if you will, of the cells. There is a slight delta between our results, especially for drag and rear lift with respect to the committee mesh. We isolated that mostly to the boundary layer resolution. It changed what our surface pressures look like on our rear deck lid and a little bit around the windshield, which that had the greatest effect on the results themselves. So it's a result that's independent of the GBMR method. It's more inherent to the overall mesh recipe differences between what we do in-house versus the committee mesh. For case 2B, very similar story. We see a very consistent delta between the committee mesh and our meshes. Our meshes, be it wake box or GBMR, show some really good agreement. But the same differences in drag and rear lift are ever present still. So it's nice that we're seeing the same consistency with the same GBMR for both geometries. So it's showing that we can actually use the same refinement volume across different geometries, which is great to see. And then looking at the deltas between the two, there's a little bit more variability in front lift. Part of the reason is where the GBMR actually shines. The difference between the wake box mesh and the GBMR mesh is actually also noticeable in how it places cells around the tire regions. So the GBMR, from the physics itself, understands that there needs to be more resolution in our tire wakes than our in-house wake box mesh alone suggested, which is part of the reason why it is closer to the committee mesh. We're getting closer to the band of what we've already seen to be important in terms of mesh resolution. So Although the GBMR and wakebox meshes are relatively consistent in their individual cases, there are certain flow features that the GBMR allows us to capture intelligently that are better aligned with what more manual mesh refinement of the committee mesh even shows. So now just to talk about some of the flow field comparisons, here's where I want to talk about some of the differences we noticed on the deck lid. I'll flip back and forth, but we'll focus on the rear deck lid first. As I mentioned, you see that we just have some higher pressure predicted. The AutoCFD mesh, we found that there was a thicker boundary layer along the rear deck lid than our in-house meshes. Again, this really comes down to the boundary layer mesh. It's not so much an effect of the GBMR. And then just some slight differences along the A-pillar and windshield, which largely has to do with the shear layers. So again, independent of what the GBMR itself is doing. Where things get really interesting and show how good the GBMR method can be sometimes in terms of clipping your mesh refinement, what each of these velocity profiles show is the black line highlights where the GBMR ends in Z, basically saying above the GBMR, it is now coarser than what the AutoCFD mesh would be here. And we can see for pretty much all of these profiles, it's basically a line-on-line prediction. So removing these cells has not been influential at all. Some of the difference inside underneath the GBMR come to some of the differences in the wheel wake refinement between the AutoCFD mesh and our GBMR mesh. But I think for us, this really highlights that our algorithm itself is actually quite good at removing resolution where you don't necessarily need it. So that's something really nice to see. And just to conclude things off, the GBMR that we generated for case 2A to knock the point home, it was able to be used for both case 2A and 2B. We saw good force, experimental force agreement between the cases, and any differences to the committee mesh were really due to boundary layer resolution. The velocity profiles that I presented show that where the GBMR is cutting away cells isn't actually problematic. It's still showing, it's basically moving those cells to areas where we need them. And the best part about the GBMR method is that it's relatively user independent for refining a CFD mesh that's actually flow physics aligned. So in our case at Multimatic, it helps take out a decent amount of guesswork when it comes to placing refinement. So I know that was quick, but thank you all very much for your time. Any questions?